This is your presenter Asloop Mudassar, and I am presenting slide number 63 of the course on laser physics. Question is, discuss the physics of radiation trapping and amplified stimulated emission, abbreviated as ASE. The answer is, consider an optically dense medium in which the spontaneous and stimulated emission processes may occur simultaneously. Also assume that a small number of atoms are in the upper level. A photon emitted by one of the atoms can be absorbed by another atom. That is, decay of one of the atoms may result in raising another atom to the same excited level. This results in the reduction of effective rate of spontaneous emission and is called radiation trapping. The increase in spontaneous process lifetime depends on atomic density, cross-section of the particular transition, and the geometry of the medium. Radiation trapping is particularly obvious in the UV regime due to large cross-section, where sigma is proportional to the absolute square of mu multiplied by nu. In the UV region, nu has a large value, that's why the cross-section is large. Increased radiation trapping means increase in the effective lifetime of the spontaneous emission by a few orders of magnitude. To describe the amplified spontaneous emission, we assume that a large fraction of the atoms are in the upper level and that the material is contained in the cylindrical form of length L and diameter d. When both ends are open, as in figure 63.1a, so let me show, for example, this figure in A, both ends are open, the cylinder has a length equal to L, having a diameter equal to capital D. Capital O is one end of the cylinder. The both ends of the cylinder in A are open. Sigma A represents the solid angle of the light emitted from this cavity. The cavity contains some material, and you see that in figure B we have closed one end of the cavity by a 100% reflector. For example, 100% reflector on the left hand side of the cavity, and the light will be emitted on the right hand side. The solid angle of the light that is emitted will be sigma B. So sigma A and sigma B are the solid angle for the case of geometry in A and for the case of geometry in B. And the caption of the figure is spontaneous emission from one face of the cylindrical shaped material with both ends open in A and a 100% reflector at the other face in B. So these two geometries can be used to observe the amplified stimulated emission. Okay, the fluorescence power emitted by the atoms around O into the solid angle sigma may strongly amplified by the active medium, which is an optically dense material. Now let's place a 100% reflector at the left face of the cylindrical cavity as shown in part B of the figure. The output will be unidirectional and the arrangement is known as basic ASE, that is a basic amplified stimulated emission. Amplified stimulated emission, being similar to laser action, has the following properties: directionality to some degree, narrower bandwidth in comparison with spontaneous emission, intense beam, soft threshold behavior. So we have discussed these properties, that is the directionality. We have mentioned these properties, that is the directionality, the narrow bandwidth in comparison with the spontaneous emission, the intense beam, and the soft threshold behavior. So let's analyze some of these properties. For example, directionality. Directionality is apparent from the figure. that is from both these figures you can see that the beam is somewhat directional, moving towards the right both in A and B, where B has improved directionality because the solid angle in B is smaller than the solid angle in A. Because in B we have a 100% refractor on the left end of the cylindrical cavity. So consider the case D is much less than L. That is the diameter in both these cases, that the diameter of the cavity is much less than in comparison with the length of the cavity. So for sigma A, that is the solid angle in geometry A, is given by pi r square over L square. And you know that pi is actually area. This is the area of the end face in cylinder A. That is in geometry A, the end face area of the cylinder is pi r square and divided by the length square. So we have a pi r square over length square, which is the solid angle definition. Substituting r by d by 2, we have this definition in terms of the diameter. So the solid angle of for the geometry A is equal to pi into d square over 4l square. Now for the case of B, look at the geometry very carefully in case of B. You see that in case of A, the beam which is originating from O, that is the O has the end of the cavity. So the light is originating as if a point source is existing at point O of the cavity. Whereas in case of B, there is a finite width of the cavity at the end face, at the left face where 100% refractor is placed. So the effective, if you look at from the center of the output region, that is from the output coupler, that is at the end, at the right end, if you take from the center, not from the in case of A, if you take center as the center of the beam and then measure the dimensions of the beam in other direction, you will get that r is the radius of the beam. But you see that in this case, r is, in case of B, r is not the radius of the beam. But you see that there is a width of the beam on the left face. So that is may be treated as equal to r by 2. So if we measure from the right face, then from the center of the not from the center of the right face, but from the center of from the originating where the beam is originating on the left face, if you calculate the diameter, the radius of the beam, then that becomes r by 2. Because there is a finite width equal to r by 2 on the left face of this cavity. So effectively the beam from the right face will have a radius of r by 2. So we are calculating the solid angle for the case B, which is equal to pi into r by 2 square divided by L square. So substituting r by d by 2, we have d by 4 squared. So expanding that one, we have a pi into d square over 16L square. So this is the solid angle for the geometry B. And you see that obviously it is clear that sigma B is less than sigma A. Refraction occurs at the exit faces of the active medium, and the external angles and the external solid angles are respectively given by. You can treat sigma A and sigma B as the internal solid angles. But you know that here we have shown sigma A and sigma B outside that one, because in the figure it is difficult to represent inside one, but treat sigma A and sigma B shown in figure 1 as the internal solid angles. But you see that for the solid angles, due to the refraction, the solid angles at the outside may be called as external solid angles, and we are using a subscript E for that. So E with the solid angle, E as a subscript stands for the external solid angle. So the external solid angle for the geometry in A is equal to pi into n square into d square over 4L square. And for the figure B, we have pi into n square into d square over 16L square. So you see that apart from the internal and the internal solid angles, and the external solid angles only differ by a factor of n square. So n square appears in the numerator of both the solid angles for the external solid angles for the same geometries. It is because you see that if you apply the Snell's law, then you see that we have a refractive index of the material within the cavity. We have n sin theta is equal to 1 into sin theta 2, where sin theta 1 is the sin theta 1 within the geometry, and sin theta 2 is the angle outside the geometry. I am not talking about the solid angle, but I am just talking about the calculation for a single ray. So for single ray, n is the refractive index within the material. We have n into sin theta 1 is equal to 1, which is the refractive index of the air, 1 into sin theta 2 for a single ray coming out from this solid angle. So for that ray, if we can replace sin theta is equal to tan of theta, because sin theta is so small that tan theta is equal to sine of theta. And then you know that we can have this angle that so tan theta can also be approximated as theta. So we have n into theta 1 is equal to 1 into theta 2. So if you calculate the value of theta 2 is equal to n into theta 1. But you know that in the solid angle we involve not only the lines but involve the areas. So for the areas, if you convert this Snell's law into the area, we have n squared into the solid angle within the cavity, which is sigma A, and outside that one we have sigma AE. So sigma AE will be equal to n square times the sigma A, and the sigma A is defined is the solid angle within the cavity. And similarly for the case B, we have sigma B external is equal to n square times the sigma B internal. So that's why we have n square factors in both of these expressions for the external solid angle, where n is the refractive index of the material inside the cylinder. The more severe the condition, that is D is much less than 1, is the narrower is the beam produced by ASE, that is the amplified stimulated emission. This will produce more narrow beam under the condition that D is much less than L. Okay, so we have described the directionality, that is the directionality is given by the solid angle over here. So we have discussed the solid angles within a solid angle sigma A and sigma B for this geometry, which is used to generate the amplified stimulated emission. We have defined sigma A and sigma B within these solid angles of the beam within the cavity, and sigma AE and sigma BE as the external solid angles to the geometry, which we have mentioned over there. For example, in these two over here. Now let's talk about, here we have talked about the directionality. The next we may talk about the bandwidth in comparison with the bandwidth of the ASME beam in comparison with the bandwidth of the stimulated emission beam. The spectral narrowing of the ASE, that is the amplified stimulated emission, is due to the fact that it has a much higher gain value at nu is equal to nu naught, in comparison with the gain value away from nu is equal to nu naught. So as you deviate from nu is equal to nu naught, the value falls fastly or quickly, but at the value of nu is equal to nu naught, the value is very high. But you see that here in this figure, that is in the figure 63.2, we are not going to plot the intensity versus the intensity on the horizontal axis, but we are going to plot the normalized intensity. So I nu is actually the intensity of the saturating beam as a function of nu, and I nu P is the intensity of the saturating beam, is the peak value of the intensity of the saturating beam. So we have I nu over I nu prime. Since I nu prime is the maximum value of the peak, is the maximum value corresponding to the peak, so this becomes I nu over I nu prime will have a maximum value equal to 1. So you see that we have shown the maximum value of all these curves equal to 1, because we are going to plot the normalized values of this one, that is I nu over I nu p, and I nu p is the peak value for these corresponding signals. And on the horizontal axis we are plotting nu minus nu naught divided by the width of these signals, that is delta nu naught divided by 2. So we are also plotting the normalized value of these frequencies on the horizontal axis. So nu minus nu naught is divided by delta nu naught divided by 2 is a normalized parameter having dimensionless quantities. So these are the dimensionless quantities plotting on the horizontal axis. The caption is a demonstration of the spectral narrowing of the amplified stimulated emission. Solid lines represent the stimulated emission for two values of gain versus the spontaneous emission lines represented by the dashed line. So ASE, that is the amplified stimulated emissions, are represented by the solid lines for these two values of gain, and the dot and the dashed line is the spontaneous emission line. So look at we have plotted ASME for two values of gain. Gain is equal to 10 to the power 6 and gain is equal to 10 to the power 3. For the gain 10 to the power 6, you can see that the beam is more narrower. That is, the spectral narrowing is more evident for the higher gain in comparison with the gain of 10 to the power 3. So you see that the dashed line has been plotted. The function is given by g of nu minus nu naught divided by gp. So the spontaneous emission profile is represented by the function g as a function of nu minus nu naught, and we have divided this by the value of gp, where gp is the peak value of g. So dividing g by its peak value will give you the normalized plot of the spontaneous emission profile. So here you can see that the spectral narrowing of the amplified stimulated emission is well evident in comparison with the simple spontaneous emission, and all these plots are the normalized plots. Solid lines in figure 63.2. So we are now describing some text relevant to figure 63.2. Solid lines in figure 63.2 show the normalized spectral profile of the ASE, where we are plotting I nu over I nu prime for two different values of unsaturated single pass gain G, and the line shapes are Lorentzian. So these line shapes in the solids are Lorentzian, and the shape of the spontaneous emission line will also be Lorentzian. Dashed line shows the normalized spectral profile. The profile represented in dash is due to function g of nu minus nu naught divided by gp of the spontaneous emitted light, where I nu p and gp are the peak values of I nu and g respectively. And you see that the two values of the gain that we have plotted, one for g is equal to 10 to the power 3, the other is g to 10 to the power 6. So this g has been obtained from the expression as explained over here. The value of the gain used in figure 63.2 was obtained from the function capital G is equal to e to the power sigma p multiplied by n2 multiplied by L, where sigma p is the peak value of the absorption coefficient, n2 is the population of level 2, L is the length of the cavity. In principle, we have in this expression n2 minus n1 instead of n2 alone, but n1 is approximately equal to 0. So we are using the gain capital G is equal to e to the power sigma p into n2 into L, assuming that n1 is approximately equal to 0. Practical values of the unsaturated gain lies in the range, that is capital G lies in the range of 10 to the power 3 to 10 to the power 6. And you see that here we have plotted the two functions for the minimum value of g, which is 10 to the power 3, and for the maximum allowed value of g, which is 10 to the power 6. Or equivalently, for the values of sigma p into n2 into L lying between the value of 7 and lying between the value of 14. and the practical values of the solid angle lie in the range. So sigma over 4 pi lies in the range 10 to the power minus 5 into 10 to the power minus 3. With these values, reduction in the line widths lies between 3 to 4 times. Intensities of ASE, amplified stimulated emission, could be Lorentzian line shape or could be Gaussian line shape represented by IL and IG respectively for the geometry shown in part A of the figure and part B for part A of the figure. You see that we may have two types of shapes for ASE: Lorentzian line shape when the broadening is due to homogeneous line broadening, and the Gaussian line shape when the broadening is due to inhomogeneous line broadening. So if there is only homogeneous line broadening, we shall talk about the Lorentzian line shape. But if there is an inhomogeneous line broadening, we shall talk about the Gaussian line shape for each of the two geometries. That is, for geometry A, we can talk about both Lorentzian line shape and Gaussian line shape with the respective intensities represented by IL and I capital G, and similarly for the second geometry. So for the geometry shown in part A of figure this, we are going to calculate, we are not going to calculate but we are just mentioning the expressions. That is IL, that is the intensity of the saturating beam. That is, you may say more accurately that the intensity of the Lorentzian profile, that is the saturating intensity in the Lorentzian profile. IL is equal to phi into IS. I is the saturation intensity multiplied by sigma A over 4 pi raised to power 3 by 2, and then after that we have G minus 1 raised to power 3 by 2 divided by G multiplied by log of G whole raised to power half. So this is the saturating intensity in case of Lorentzian line shape for the geometry A, because we are using over here sigma A as given in equation number 63.1. And for the Gaussian saturating beam for the same geometry, that is for geometry A, we are going to give you I capital G, that is the saturating beam in case of Gaussian profile is IG is equal to phi into IS, and then we have sigma A over 4 pi. The factor that differs is the power that is raised to 1 over here, but this is raised to 3 by 2 in case of equation number 1. So for equation number 2, we have for the Gaussian intensity, saturating intensity, that is equal to phi into IS into sigma A over 4 pi multiplied by G minus 1 raised to power 3 by 2, and then G into log of G, both raised to power half as in equation number 2. So we have given these two expressions, that is IL and IG, for the geometry shown in A. That is the geometry over here, that is the upper geometry. So we have given the saturating intensity for the Lorentzian case and for the Gaussian case for the geometry A, where phi is the fluorescence quantum yield and Is is equal to h nu naught divided by sigma t into tau is the saturation intensity of the amplifier at the transition peak. When L becomes comparable to Is, when when I, that is the intensity, that is the IL or Ig we have mentioned just, when IL or Ig, which we generally call as I, becomes comparable to saturation intensity Is, the amplified stimulated emission becomes dominant mechanism, depopulating the available inversion. Thus for I is equal to Is, which means that IL is equal to Is and Ig is equal to Is. For G much greater than 1, the threshold peak gains becomes. So now we are going to calculate the gain, but gain calculating from this equation, we are assuming the condition that G is much greater than 1. This is the one condition. The second condition is that IL is equal to IS. So IL and IS will be cancelled out, and we have 1 on the right hand side, and here we have g raised to g minus 1. Since g is much greater than 1, so we have only g raised to power 3 by 2, which will be cancelled by the g raised to power half from the bottom, and we are left with only one capital G at the numerator and log of g in the denominator. So rearranging all these values over here, we have GL from this formula, which is equal to 4 into pi raised to power 3 by 2 divided by 5 into sigma A, and then we have log of GL raised to power half. We are using over here GL because we are talking about the Lorentzian gain obtained from this formula. And if we want to obtain the same relationship from equation number 2, we shall call it as GG. That is the gain in case of Gaussian profile. And again, in this relationship, to obtain this relationship, we have used IG is equal to IS in this case. And again, capital G is much greater than 1, and we are labeling this capital G by capital GG. So we have written down this relationship after simplification. So this is the gain due to Lorentzian line shape in case of geometry 1, and this is for the case of Gaussian profile for the same geometry, that is geometry A. Now for the second geometry shown in part B of figure 63.1, the above relationship can be obtained by replacing the single pass peak gain capital G by the double pass peak gain G square and sigma A by sigma B. So making the arrangements that is representing sigma, capital GL by second pass, which is GL square, and similarly GG square, and sigma A will be represented by sigma B. For the second geometry, we have the relationships obtained from 63.3 and 63.4 respectively, shown in 63.5 and 63.6. And we have replaced capital G L and capital GG by capital GL square and capital GG square in equation number 63.5 and 63.6, because we are here talking about the double pass peak gain, because we have placed a reflector at the other face of the cavity shown in B. On the left hand side we have a 100% reflector. Okay, so we have calculated the gain for both of these geometries for the case of the Lorentzian and the Gaussian cases respectively. To obtain more directional and more narrow bandwidths of the amplified stimulated emission radiation of high intensity, the second scheme in part B of the figure this is used. That is, for more directional beam, for more narrowing bandwidth of radiation and with the high intensity of the radiation, we can use the geometry shown in figure part B in comparison with part A. So B could be preferred. Okay. Amplified stimulated emission systems use either single mirror or no mirror at all, and are called mirrorless lasers. ASE limits the maximum inversion that can be stored in high gain pulsed amplifiers. So you see that ASE provides a limit in those cases where we are going to obtain a high gain profile in pulsed amplifiers. ASE contains amplified spontaneous emission noise and has some spatial and temporal coherence properties much different from the coherent properties of the lasers. ASE also plays the role of dominant noise term in erbium doped fiber amplifiers. So you see that we have just mentioned a few characteristics of the amplified stimulated emission. this is the end of slide number 63.